ever feel like deep learning is kind of, this mysterious thing? Like it's all tech jargon and you'll never get it.
Yeah, it can definitely seem that way.
But today, we're going to try to clear the air a bit, right?
Yeah.
We're diving into Grokking Deep Learning.
Great book.
Yeah, to uncover those aha moments.
Absolutely.
And the best part is, you don't need a PhD in math to follow along. Trust me.
It's more about concepts than, complex equations.
Exactly. And this book, it really does a fantastic job of making even the complicated stuff feel surprisingly simple. Like it starts with this idea of the predict, compare, learn cycle, which, it sounds kind of technical when you say it like that.
Right.
But something we actually do all the time in our everyday lives.
Absolutely, yeah.
It's like imagine a kid, right, learning to throw a ball. They throw it, they see where it lands, and then they adjust their throw the next time based on how far off they were.
Exactly. They're constantly comparing, adjusting.
And it's the same with a neural network. It makes a prediction, sees how accurate it is, and then uses that information to fine-tune itself.
It's a continuous feedback loop, always learning and refining.
So it's always trying to get better, like it's never satisfied.
Exactly. Now, let's picture this. A simple neural network.
Okay, I'm picturing it.
And its only job is to predict what movie ratings you'd give to new movies.
Okay, so like how those streaming services seem to know what I want to watch before I do.
Exactly. They're already using this kind of technology.
It's kind of creepy, but also kind of cool.
Right. Now, imagine this network is taking in tons of inputs.
Tons? Like what?
Like what genre the movie is, who directed it, even your mood that day.
Wow, my mood. That's pretty specific.
All those factors can subtly influence what you enjoy watching.
True, true. But how does it know what to do with all that information?
That's where the magic of weights comes in.
Weights? Like dumbbells?
Not quite. Think of it like this. You have an old-fashioned radio.
Okay, I have one of those somewhere.
And you're turning the knobs to adjust the volume of different frequencies.
Get that perfect sound, yeah.
Exactly. Weights in a neural network are like those knobs.
Interesting.
Each connection between the inputs.
Like the movie genre, my mood, all that.
Yep, and the output, which is your predicted rating.
Okay, got it.
That connection has a weight that determines how much influence that connection has on the final prediction.
So, like, if I always say I hate romantic comedies, the weight on that connection would be?
It would be adjusted to steer the predictions away from romantic comedies.
Ah, that makes sense. But what if the network keeps messing up? Like, what if I keep giving those cheesy rom-coms 5 stars?
Well, that's where backpropagation comes into play.
Backpropagation sounds intense.
It sounds way more complicated than it actually is.
Okay, good. Because my brain is already starting to hurt.
Basically, it's like, imagine the network realizing it made a mistake, right?
Okay, so it's got some self-awareness.
Kind of, yeah. It's like it's saying, whoops, I predicted a 5-star rating, but they actually hated it. And then
it has to figure out what went wrong.
Exactly. So it goes back through all those connections and weights we were talking about.
Oh, right. Like retracing its step?
Precisely. It's like, okay, did I give too much weight to the romantic comedy genre? Was I not factoring in their mood enough?
And then it adjusts those weights accordingly.
You got it. There's this cool method it uses called gradient descent.
Gradient.descent. Okay, now you're just messing with me.
I promise. It's not that bad. Imagine you're trying to find the lowest point in a valley, right?
Okay, I'm picturing
Each weight adjustment is like taking a small step downhill.
Getting closer and closer to the bottom.
Exactly. And that lowest point, that's the optimal configuration for making accurate predictions.
This is blowing my mind, but in a good way. The book does a great job of explaining it all with visuals, which helps a lot.
Yeah, visualizing a neural network makes a huge difference.
It's like instead of it just being this abstract idea, you can actually see it with all the nodes and connections.
Exactly. You can see how the information flows through the system.
It's like suddenly understanding the blueprint of this complex machine.
Precisely. But there's more to deep learning than just processing information.
There is.
Oh, yeah. It's not just about crunching numbers.
Okay. Because my brain can only handle so many numbers.
There's this crucial concept called generalization.
Generalization. Sounds important.
We don't want a network that just memorizes the data we feed it.
Right, like a parrot that can repeat phrases, but doesn't actually understand what they mean.
Exactly. We want a network that can actually learn from the data and apply that knowledge to new situations, to new data it's never seen before.
So it's like we want it to be able to think for itself, basically.
In a way, yeah. Think of it like this. You don't just want a student who can ace a test by memorizing all the answers.
You want one who actually understands the material.
Yeah. Exactly. Someone who can apply their knowledge to solve new problems, to think critically and come up with their own solutions.
Okay, that makes a lot of sense. But how do we actually make sure a network doesn't just become a memorization machine?
That's where techniques like dropout and regularization come in.
Dropout. Sounds kind of harsh, like we're punishing the network for getting things wrong.
It's not like that. It's actually more about helping it learn better.
Okay, I'm listening. Explain it to me like I'm 5.
All right, so imagine a basketball team, right? And they're practicing, but the coach makes them play with only 4 players on the court instead of 5.
To make it more challenging.
Exactly. It forces those 4 players to step up their game, to become more versatile and adaptable.
Because they have to cover more ground, right?
Right. And in a similar way, dropout means randomly turning off some of the connections in the network during training.
So it's like we're benching some of the players.
Exactly. It forces the network to find different paths to a solution, to not rely too heavily on any one connection.
So it's like building redundancy into the system.
You got it. And that makes the network more robust and less likely to overfit to the training data.
Overfitting. That sounds familiar.
We talked about it a bit earlier. Remember, it's like that student who aces the practice test but then bombs the real thing.
Because they haven't really learned the material, just memorize the answers.
Exactly. And dropout helps prevent that.
Okay, that makes sense.
Oh.
But what about regularization? What does that do?
Think of regularization like adding a penalty to complexity.
Okay, so like those teachers who take off points if your essay is too long-winded?
You got it. Basically, it discourages the network from developing overly complex connections during training.
Why is that a bad thing?
Well, imagine the network is trying to explain every single data point in the training set, even the outliers, the random noise.
It's trying too hard to be perfect, even when it shouldn't.
Exactly.
Yeah.
It creates these really intricate, convoluted connections, which might work great for the training data.
But not so much for anything new.
Right. It becomes too tailored to the training data and can't generalize well.
So regularization is like saying, keep it simple, stupid.
Kind of, yeah. It encourages the network to find simpler, more elegant solutions that are more likely to translate well to new data.
So it's like finding that balance, right, between a network that's too simple to be useful.
And one that's so complex that it only understands what it's already seen.
Exactly. It's like Goldilocks trying to find the porridge that's just right.
I like that analogy, and the better we understand how to strike that balance, the closer we get to building truly intelligent systems.
This is fascinating stuff. We've covered a lot of ground here, from the basics of how neural networks learn to these more complex concepts like backpropagation, dropout, regularization.
It's a lot to take in, but it's all connected.
It's like we've peeked behind the curtain and started to understand the magic behind deep learning.
And we haven't even gotten to convolutional neural networks yet, or recurrent neural networks.
There's more.
Oh yeah, we're just getting started. But those are topics for another deep dive.
Well, I'm already hooked. But for now, let's take a quick break and then we'll come back and talk about CNNs, RNNs, and everything in between.
There must be times when, these networks they hit a wall.
Oh, absolutely.
Like the book talks about overfitting.
Right.
Which, I don't know, it sounds kind of ominous.
Yeah, it's a big one. It's a common pitfall in deep learning,
Like what happens? What does that even mean?
So imagine that student, right,
Okay.
who just aces every single practice test.
They've got it down.
They've memorized all the answers,
Right.
but then come exam time, they totally blank.
Because they can't rely on memorization.
Exactly. They haven't actually learned the material.
Oh, I see.
They just learned the specific examples they were given.
The practice tests.
Yeah. And so a network can fall into the same trap.
It can get too comfortable with the data it's seen.
Yes. It becomes like overly familiar with the training data.
It's learned all the quirks and the, what do you call them, idiosyncrasies? Yeah, all the little details that might not actually matter in the grand scheme of things.
Right. So it's not seeing the forest for the trees.
Exactly. And it might do amazingly well on the training data, like really, really well.
Because it's memorized it.
But then you give it something new, something it hasn't seen before.
And it just falls apart.
It can't generalize,
It's like it's got blinders on, only focused on what it's seen before.
That's a great way to put it.
And that's a problem, right? Because we want these networks to be able to handle new situations.
Exactly. The whole point of deep learning is to build models that can generalize, that can deal with the real world.
Which is messy and unpredictable.
Exactly. So overfitting, it's like this big obstacle we have to overcome.
So how do we fight it? What can we do?
Well, we've already touched on a couple of techniques. Dropout and regularization,
Right, right. Those were...
There are secret weapons in the fight against overfitting.
Okay, so remind me again, how does dropout work?
So remember the basketball analogy?
With the benched players?
Yeah. So with dropout, we're essentially doing the same thing, but with the network's connections.
We're randomly turning off some connections during training.
Yes. And that forces the network to adapt, to find different pathways to a solution.
So it's less reliant on any one connection.
Exactly. And that makes it more robust, less likely to overfit.
Okay, that makes sense. And then regularization. That was...
Regularization, it's like we're telling the network, hey, keep it simple.
Don't overthink it.
Right. We're basically adding a penalty for complexity.
So the simpler the network, the better.
Well, not necessarily the simplest, but we want to discourage it from getting overly complicated.
Because that often leads to overfitting.
Exactly. Think of it like this. Let's say you're trying to draw a picture.
Okay.
And you're using a really, really fine tip pen.
Okay. Very detailed.
Yeah, and you're trying to capture every single little detail, every imperfection.
So you can get lost in the weeds.
Exactly. You might end up with a drawing that looks exactly like what you were copying.
But it won't be very good.
And it won't translate well to other things.
So it's like that with regularization.
Yeah.
We're telling the network to use a thicker brush, so to speak.
Yeah, in a way, we're encouraging it to find the broader patterns, the more general principles.
Instead of getting bogged down in the minutia.
Exactly. And that makes it more likely to generalize well to new data.
This has been incredible. We've learned so much about deep learning, from the basic building blocks of neural networks.
To these really powerful techniques for training them effectively.
And we've only just scratched the surface. It's amazing to think about all the potential applications for this technology.
It's already transforming so many industries, and it's only going to become more prevalent in the years to come.
So if you're listening to this and you're feeling inspired, don't stop here. There are so many resources available to help you dive deeper into the world of deep learning.
Take online courses, read books, experiment with different algorithms.
The possibilities are endless. And who knows? Maybe you'll be the one to make the next big breakthrough in AI.
That's what I'm hoping for.
Me too. And on that note, we're going to wrap up this deep dive into Grokking Deep Learning. Thanks for joining us.
Thanks for having me. It's been fun.
Until next time, keep learning, keep exploring, and keep asking those big questions.